Hi, and welcome to my talk. I'm Francois Scharffe. I'm a co-founder and knowledge engineer at 3Top, which is a small startup doing a ranking and recommendation website. We're not yet launched, and I will say a few words about it anyways, and I will tell you about word embeddings as a service. Many of you probably have already heard about Word2Vec. So we're going to talk about it and how we use it in production to do recommendation and related stuff. So I will present the startup quickly and what are word embeddings and how do we implement a simple recommendation system for 3Top categories. So what is 3Top? 3Top is a ranking and recommendation social media where users go and enter the top 3 ranking in the category of their choice. So the idea behind it is to get rid of the star rating system by saying who cares about 3 stars and less. We are only interested about the highest star rating, and we're also not really interested about reading through a lot of reviews, but we're really interested in finding the best stuff, right? And that's valid for restaurants, that's valid for stuff on Amazon, that's valid for movies, any category really. So we're also oriented towards getting recommendations from friends. And so why 3? Because, and why not 10? So good question. The idea is actually, if you have more than 3, then you can probably come up with a more refined category, more specialized category to rank stuff. So I will show you a few examples. Now, okay, here are a few screens, so you might not be able to read here, but it's a search for 1980s vampire movies, and then finding ranking in the middle screen for that category, and then on the right is picking up an item there and getting some information about that item. So you can rank really anything and everything. So for example, here's a ranking about places. That guy, Joseph, ranked his 3 top gyms for students near the Lower East Side and gave his 3 top there. A movie, 3 top movies about Wall Street. And here's the ranking by Michael, my other co-founder. And then 3 top foods named after people. Okay, so really you can go crazy and rank whatever you like. And so what you might see is there are pictures and other information related with the items. And so that's what we're trying to do, is to understand what are the categories that are entered by the users and what are the items in these categories. So the users just enter free text categories by typing the categories. They type the items in this category, and we try to understand what is there inside. Okay. So for that, we have a data engineering pipeline where we are doing NLP to process the categories. So we parse categories. We first developed our own parser. We are currently switching to Spacey, which is a great library. If you don't know it and you're doing NLP, it's a great Python library. We're also doing name entity recognition and linking. We're detecting location in categories. And so we have a knowledge graph backed by an ontology, and we're trying, so we have this itemization pipeline that takes what we understand from the category, takes the items, and then try to match those items to an entity in the knowledge graph. Okay, and once we have that, okay, we have a much richer data infrastructure to do recommendation, to present more information to the user as well, to do auto-completion, to do various tasks.
What's an example of a category?
So here were a few examples. So movies about Wall Street is a category. Foods named after people are a category.
I just type that in myself. I don't pick from a list or anything.
Yeah, so it can be either you type it yourself or you get it from a friend and then you will react, right? So a friend of yours shared that category, shared this ranking, and you will say, oh, my 3 top movies about Wall Street is actually not that. So you re-rank. So that's, you can agree here or re-rank the thing. And so in that case, you won't type the category.
And does every new category make it into the system?
Every new category makes it into the system, yeah.
Thousands and thousands.
Yeah, so you will see, we're not yet launched formally, so we're hoping for thousands and thousands, yes. So here is an illustration of what I was talking about. We have this knowledge graph in the middle, and we're by these pipelines we're relating items and categories to the knowledge graph. For categories, we try to identify what the main concept for the category is and relate that to the knowledge graph, and then through it relate items to various APIs. So we use DBpedia, we use Wikidata, Yelp for places, etc., etc. Okay, so now let's go to the matter of the talk. So what we wanted was a recommendation engine, a simple recommendation engine that it would be more accurate to call a related engine. So when you're on a category page or on a ranking page, it will recommend you related categories. The problem is, look at those impressive figures. We have 300 users, 2,100 rankings, and 1,300 categories. So doing collaborative filtering on that would not, and especially because of the open-ended thing of the system, we have categories in a lot of different spaces and or topics, and so collaborative filtering wouldn't work. And so, yeah. Big data. So we heard about Word2Vec, and so we gave it a try, and it's something that worked pretty well, that we are pretty happy with. And so I will present you how we developed that recommendation engine and how we're using it in production. So who hasn't heard about Word2Vec here? A few? Not many. Okay. All right. So Word2Vec is an implementation. It's an algorithm to realize a word embedding. And word embeddings allow to represent words in a high-dimensional space in a way that the words appearing in the same context in the training corpus will be closed in that space at the end. So when I'm saying high-dimensional, it's not that high-dimensional. It's in the hundreds of dimensions. And yeah, that's it. So a few quick comparisons. So compared to bag of words, the dimensionality is low and constant with regard to the vocabulary size. So you set up the number of dimensions you want in your word vectors prior to the training, and the dimension will remain constant. And then, depending on the training algorithm you're using, you will get partially learned models giving you partially good results, which can be good if you want to experiment with different corpuses, for example. Compared to topic modeling, I say better granularity because the base element is the word, but really, that's what I wrote, but really it's a different thing you're studying. You're studying, so in both cases you have a corpus, but in one case you're studying what are the documents, what is the meaning of a specific document in a corpus in the corpus for topic modeling, where here we're really studying what is the meaning of the words in my corpus. Okay, so it's a different granularity. Something to mention is that there are extensions to Word2Vec that learn phrases, so or documents, so that take into consideration the order of the words, okay, in sentences. We're not there yet, so I will not talk about it. So what are word embedding models good at? They're good at modeling similarity between words in a continuous manner. So similarity between tomato and beefsteak will be lower than the similarity between an apple and a tomato, which will be lower than a similarity between a pear and an apple, okay? And then you can take your vectors and then do algebraic operations on this word vector. So, the vector of Paris minus the vector of France will be similar to the vector of Berlin minus the vector of Germany. And I will now show some examples directly using the most popular library in Python, which is the Gensim library that has an efficient implementation of the training algorithm for word2vec. So we're using here a glove model. So it wasn't trained with Gensim and word2vec, but with another training algorithm called glove. So we are reusing this pre-trained model very easily by loading it into the from the Gensim library. And then we are querying that by asking the most similar words for the word Python. And we've got the list here, so I can read for those who can see. I have Monty, PHP, Perl, Cleese, Flipper, Ruby, Spamalot, JavaScript, Reticulated, and Monkey. So for those who know Monty Python, this should be pretty clear. So some other examples. Now I will combine two words, Python and programming, which will do an average on the vectors, and then build that virtual vector and try to get the closest vector to that virtual vector, and I get Perl, scripting, scripts, PHP, and language. Okay, so here is an application, disambiguation. Okay, that's very straightforward. Another example, if I do Python in Venomous, then I get results in the snakes and spider domain, okay? All right, and so now the most classical example that you will find on every blog and every paper in the literature, this is the analogy example. So man is to king what woman is to X, and ask the question. And so we can do that very easily as well. And I see that indeed the result is queen, but the other results are also interesting. So monarch, which is like a non-gendered version of king and queen, and throne, we can also be understood in that same context. So now, how about training a model? So it is very easy once you have a clean corpus given the libraries and tools that are available in Python. There are very good tutorials on Gensim. There was also a talk last year at PyData in Berlin about Radim Rerek, who is the author of Gensim, and especially the interesting part is the optimization in Cython that make it very efficient. There is also a library for glove, which is more experimental, but there are also some interesting pull requests that you can check that make it actually pretty efficient. So to tell more about the implementation specifics, the training time for a 1.9 billion words corpus, which start to be interesting, is 8 hours on an 8 proc and at 8 threads to learn a 600 dimension model. The memory requirement in Gensim is linear with regard to the number of dimensions and the size of the vocabulary. The glove implementation is faster, but as the original Python implementation has quadratic memory size, but again, there are some pull requests for optimizations in here. So glove has that nice feature that if you stop the training, you already have some partially good results compared to word2vec that requires that you complete the training in order to get some good results. Something to mention again is that in Gensim, you can always keep training a model. So if your base corpus evolves over time, you can always refine your model by adding more sentences to your model. So that's a nice feature. One good thing to know, in general, the bigger your original corpus is, the better results you will get independently on the task you're doing. So if you throw more data into your model, you will get good results. So you will, yeah. So you would say, oh, okay, then I take the biggest model that was trained by the author of glove or word2vec, and I'll be fine. So what you might want is to actually learn things about your corpus, and in that case, then you rather train your own model on your corpus. So, or if you want to, for example, compare two different parts of your corpus, see how the vocabulary, the meaning of words change, in that case, you'd rather go and train your model yourself. So in our case, because of the very open-ended task we're having, we're reusing a corpus from glove. So we compare different trained models, and we put those on GitHub here. You can check there's a list of different models with lots of different columns there that we cannot see that tell you what was the training algorithm and etc. So if you're interested, we are currently using this common crawl 42 billion words corpus with 300 dimensions that give good results. So when we did not try that, this bigger 800 billion words, corpus yet. Okay. So now we've got our model that is trained already, and we want to do recommendations for our categories. So it's pretty straightforward. What we're doing is we're taking the words appearing in the categories, and then we combine the vectors to get a new vector that will be a category vector. And then we do that for every category on the website. And we get this category space, and then now we ask for most similar categories in this space. So what are the closest categories around the category? Okay. Yep.
Can you give an example there? Sorry, I got kind of lost. What is the recommendation that you're doing if I type in 3 top mystery movies?
Yeah. Yeah. We're coming to that. Yeah. So what we try different techniques. So we try to keep only the main noun or main noun phrase in a category. But at the end, what works well for us is to keep everything that is not block words, stop words, basically, so noun, verbs, adjectives.
What do each of the tags stand for?
Those are post tags, so noun, plural noun, adjective.
JJ is adjective?
Yeah. I might not be able to give that one. The NNDBN is in case we detect a name entity from DBpedia, for example. So we have extended that. Those are not canonical. All right, so then we put those vectors in a category space, as I just said, and getting the similarity between two categories is just doing a dot product between the two category vectors. So let's look at some examples. This one doesn't display very well, but it's blue color beers that come in a can. And we get, as a result, I can maybe put it a bit bigger. No. As a result, we get Belgium Trappist beers, Belgium Beer Cafe in NYC, Dark and Stormy cocktails in NYC. So, given the amount of categories that we have, this is really good results. What is very interesting is, so dark and stormy cocktails in NYC, which is semantically somewhat related to blue-collar beers because it's about drinks. But as you can see, none of the words are the same, right? So that's one of the good features is that it really finds synonyms and more.
Quick question for you.
Yeah.
The reason it's just a dot product and not like a cosine similarity is because the vectors are already normalized, correct?
Yes.
I guess are the vectors, like when they come out of the word2vec model, are they like, do they have a length and magnitude of 1?
Yes, they're normalized. Yeah.
Okay.
Yeah. Another example, Italian restaurants in NYC. So Italian restaurants in New York, restaurants in NYC, NYC Mexican restaurants, etc., etc. And finally, Coen Brothers movies. We get Quentin Tarantino movies, Martin Scorsese films, movies starring creepy children, etc., etc. So we have some funny categories. I invite you to check it out, freetop.com. Yeah, and again here, Coen brother movies and Martin Scorsese films, films and movies are synonyms. You might, using other techniques, like WordNet, you might find that they are in the same scene set, etc. But it really is a much simpler way of doing similarity. So we're using the command crawl, 42 billion words. So command crawl is for those who don't know, is a partial crawl of the web. It's an open data effort to trying to provide web crawls that can lead to search engines like DuckDuckGo, for example, is based on the command crawl. So we have words coming from everywhere. A good thing about this corpus as well is it contains also a lot of bad data, like words containing spelling mistakes, things like LOL or LOOOL, or so all these kind of funny words you find on the web. And this is interesting because that's what our users do. They enter words, but they are in the corpus, so that's interesting. So what is taking 6 gigs of memory is the word-to-vec model, that learned word-to-vec model.
Didn't it say 1.9 gigs in the previous?
That was the number of words in the corpus. Now I take about the size.
It's really 6 gigs, that file.
Yeah. So we're using our app, our site is in Django. We're using Celery. And until recently, we had Celery and Django working on the same EC2 micro instance. So there's no way we can allocate all that memory for our service. So that's when we decided to build an API for this word embedding that we could query and then would return us. I'm sorry if we don't see the bottom of the slide. So we can query that, and it returns us so we have different methods there. So it's a simple Flask server that you access word-to-vec similarity between word 1 and word 2, and similarity if you want different words. We have a model keyword. Oops, sorry. We have a model keyword that will return you the model for a word, and it's easy to set up. You just pass. I don't know if you can see it here. You just pass the model as an argument, and then you get a server providing you a word-to-vec model.
Aren't you just using a basic case, though, where you take the mean vector for each category and you query it for the most similar mean vectors?
Are we using...
So here, like, you have all the canonical cases of word-to-vec as is implemented in Gensim.
Yeah. Mm-hmm.
But for your use case, you just want the most similar category, right?
Yeah.
And the way you're doing that is you're taking the mean word-to-vec vector.
Yeah.
And then you're taking the mean word-to-vec vector for all the other categories.
Yeah.
You're computing dot product.
Yeah. Yeah.
So why is all the extra stuff?
Oh, that's true. That's just... so I wrote a service. It doesn't cost much to provide that as well. Before publishing that, it makes it easier for people, I guess.
Okay.
So that's our architecture. I won't talk a lot about it. Just so we have this word vector space word similarity service. If you're interested, I can tell you more. Basically, there's Django instances, Celery workers. We're all in the Amazon realm. Okay, so now we have a few categories in the space, but one thing we're planning to do is to pre-generate a lot of categories to make it even better, like even easier for the users, having more like autocomplete features. So, that will make the size of the category space itself increase. So for 1,000 categories, we have a 2 megabyte category space, right? So it might be confusing here, right? On one side, there's the word-to-vec word model that we're using to build a category model, okay? So there's two different things. And so that category model is currently kind of small, so we have it in memory in each worker, but it might get bigger. So what we're doing, we're so storing the category vectors in the SQL database as a Django object as part of the category, a Django object. For that, we're serializing the NumPy vector as a base 64 encoding, and I'd be glad to have feedback on that.
Why aren't you just storing it as a string, like the vector in MySQL?
Because I don't know how. Well, we can discuss that later. I'd be glad. I don't have much argumentation for that. So we're defining this vector property on the category model with a get and a set that will, encode and decode the vector when we need it, and so we can get the. I guess that there's no NumPy array in MySQL, right?
No, of course, but like I ran into this. I did the same thing in my work, and just Googling like how to store an array with floating point values in a SQL store. Like most people recommend it just to store it as a string.
To store it as a string,
Yeah.
which is what we're doing.
Right, but you're encoding it first.
Oh, okay, okay.
I suppose there's not much of a difference.
It is.
It didn't look like it though, because it looked like this huge thing. But you might be right if it's 300 dimensions and they each have a bunch of decimal numbers.
So, all right, so we're doing that, and then the second thing that we're doing in order to not query the database each time, we're using memcache to cache that category space. And so we have each vector cached with its own key, and then the indexes for the model cached with one key for each index. Okay, so that allows us to, yeah, okay. So, and now when we update each process, so each process has its own copy of the vector space, and then whenever a new category is added, the cache is updated and then signal to the processes, the workers to reload from the space, okay? 10 minutes, all right. So this is a work in progress. So I was telling you we're planning to add these hundreds of thousands of categories, and now this category space will become large. We cannot anymore tolerate having each worker having his copy of the space. Similar thing that happened with the original model. So my guess is that we will put that on a server again and have that as a service, and then do some caching at various levels, not to have to query that service too much. Now, what we're also planning to do is to include entity vectors, so to learn entities vectors, so currently, if you have New York City, you have 3 words, New York and city, and each have their own context, and combining them is not as good as having one entity, New York City, that is learned as it in the corpus. Okay, so there are techniques to do that. It's a bit more problematic to do that at large scale, but we're going to try that. Another thing we're planning to do is to train a specialized corpus now by scrapping a lot of treetop-like best things like categories all over the web, and to train a corpus based on that, and also train a phrase-to-vec or document-to-vec model on these categories that remember the order of the words. And a last thing that I didn't mention is that once the category space becomes large, getting the similarity becomes slow. And so I've heard about the Hanoi library that allows to do approximate approximate similarity in the space, and we're also planning to try that. I put some few resources, so linked to various blog posts that I find interesting on the topic, and as well a few academic papers. Especially, I recommend you the papers from Levi and Goldberg on that topic. They are not authors of Word2Vec nor Glove, but they discuss their relationship, and it's very interesting. That's it. Thank you.
How did you combine words in a title to create an overall vector?
Words in the title?
Yeah, how did you combine the vectors, like when you found words that are nouns, adjectives, or verbs, and you have a vector for each word? How do you combine those vectors?
We do a simple mean on the vectors.
Did you experiment with different ways?
Not much. I read that there are different possibilities. You can add vectors simply. You could even concatenate vectors, but you have the problem that then different categories will have different size, so it doesn't help really. But yeah, sum or mean is what I saw. Sorry.
What duplication of the topics? Like when people ask like top things to do in New York or whatever, how do you have like somebody that puts a question mark or a full stop, like the topics themselves? You said they're freeform, right?
Yeah.
So
how do we clean up the categories that people enter? Right. Yeah. Okay. Yeah. We're doing a little cleanup, but we still have a way to go. So to correct typos. We're using actually Google spell checker. We're title casing categories. We're removing dots, that kind of thing. Nothing fancy. Sorry, there was a question before.
For the pre-talk one that you gave that has a list of different Word2Vec implementations that you found helpful, are there any phrase-to-vec implementations on that list? Or
yes, so Gensim actually has a phrase-to-vec, doc-to-vec implementation. Yes, it is in Gensim. Oh, no. So for models, no. So surprisingly, I don't know about any model that is trained with a doc2vec. And I'd be glad if anyone knows about it. I'd like to try that.
Are you positive there's no pre-trained one in Gensim? Or on Google's, that kind of clean, raw site that Google has with the links to the pre-trained?
Yeah, they only have word models.
Can you talk a little bit about your approach to incorporating named entities into the model?
Yeah, so in the original Word2Vec implementation from Google, there's this thing where you can do multiple passes, and there's a count of how frequently words are collocated, and by setting a threshold, you will do a second pass and consider those as an entity, and it will so. But this is kind of fake, right? It's purely statistical. So I guess it kind of worked. So that's one first approach. A second approach, which is much more problematic, I would say, is to first do some name entity recognition on your corpus, and then tag those entities, and then do the learning. The problem is if you are in multiple tens of billions of words, it starts to be very expensive, and so yeah. To do the name entity recognition, yeah.
If there are no more questions, could you go back for the sake of the video and show each slide for about a second or two?
Which slide?
From the beginning, just a couple of seconds of each slide.
Every slide?
Yeah. How many slides are there?
30?
It'll take a minute.
Is there any... can I talk as well? Okay. If there's any other question, I can still take some. Yeah.
To continue following up on that last question, have you tried the built-in Word2Vec entity recognition, and does that work well?
No, I haven't. Okay. To be honest, I know. So you can download the Google corpus, the Google News pre-trained model, and you'll see there are name entities there, and yeah, I mean, I didn't extensively tested it, but New York City is there, cities are there, famous persons are there. Yeah. There's also a Freebase model that is trained on Freebase entities there, so that might be also something to consider. And there are various, like, this is a, famous hype topic in NLP, and people are trying a lot of various things, so it's kind of hard to follow, but I know the DBpedia people are working on training DBpedia vectors. So that correspond to topics or Wikipedia, topics, entities.
You said you had generated several 100,000 possible categories.
Yeah.
How did you do that?
So we're using Wikipedia categories.
Okay.
And then based on our ontology, we define, in the ontology, especially for places, we define lots of kind of types. Like, for example, we have all sorts of restaurants, Italian restaurant, pizzeria, we have a Brazilian restaurant, also. And we will combine that with cities, okay? So 3 top Italian restaurants in New York, 3 top Italian restaurants in the West Village, 3 top aquariums in Chicago, so just extensive generations or generation of categories like this. Is the speed okay? Can I go faster? Or?
You're good.
I'm good?
Yeah, you're good.
Okay. All right, thank you then.